in this section we are going to explore infinity and beyond. So this infinity and beyond is divided into 4 parts. So first part is about cardinality. So we will see what cardinality means. Once we know what cardinality is, we will actually see the cardinality of some of the big sets. So for example, natural number set is a big set. So we will count the number of natural numbers. So after this part, Rajnikant will not be the only person who can count up to the infinity. You will also be able to count up to the infinity. Then other than natural number, we will explore the number of even numbers, odd numbers and rational numbers. In third part, we will see Cantor's general theorem. So we will prove the Cantor's general theorem and then we will see its implications. So the third part is the optional part, but to understand the fourth part better, I will recommend you to watch the third part also. And in fourth part, we will see degrees of infinity. So actually Rajnikant counted up to infinity thrice yesterday, but due to unawareness or due to lack of interest, he did not went past the infinity. So in fourth section, we will try to explore what lies beyond infinity, and then we will be able to see the degrees of infinity. We already know the concept of cardinality. The cardinality of set is defined as number of elements in set. So for example, let's say A is my set which has element A, B, C, D, E. So the cardinality of set A is number of elements in set A. So 1, 2, 3, 4, 5. So cardinality of A is actually 5. So for smaller set, the cardinality of that set is very obvious concept. But what will be the cardinality of bigger set? That is our topic of interest. But before we move ahead, let's try to understand one more concept which is called as same cardinality. So what is same cardinality? So two set has same cardinality if number of elements in both sets are equal. So for example, let's say I have set A 1 which consists of some marbles. And then I have some set B1 which consists of some boxes. Now I want to find out whether the set A1 and B1 are same cardinal sets or not. So without actually counting, how we can find out whether these two are having same cardinality? So what we will do, we will map first element of set A with one element of set B1, another element of A1 with another element of B1, next one and the next one. So after finishing this mapping, we will come to know that there is one extra element in set A1 which is unmapped. So we can conclude that A1 ka cardinality is greater than B1 ka cardinality. So now assume that there is one more element in set B1. Then we can map the extra element of A1 with this element. And once we finish this mapping, we will come to know that this A1 and B1 are same cardinal. They are having same cardinality. So this mapping is something particular. So what is the property of this mapping? Every element A1 has associated element in B1. So no element in A1 is unmapped. Similarly, no element in B1 is unmapped. And thirdly, no two elements in A1 are mapped to the same element in B1 and vice versa. So I will avoid jargon for this kind of mapping and I will call this mapping as a perfect mapping, one for one, man-to-man marking. So this is a man-to-man marking. So I will call this mapping as a perfect mapping. So even while counting the number of elements in A, what we have done is we have assigned number 1 to A, number 2 to B, number 3 to C, number 4 to D and number 5 to E. So what we have done here, here also we have found out the mapping between these two sets. So I will call this set as n1. So this is some subset of natural numbers. So what I have done here, I have used some subset of n to count the number of elements in A. So what is the process of counting? Process of counting is actually finding the mapping of this kind. So for example, let's say I want to count the number of elements in one set. What I will do, I will consider set n1, which is subset of n, which will contain first n natural numbers, and then I will map one element of A with number 1, another element of A with number 2, another element of A with number 3, and so on. So establishing a mapping gives me the cardinality of that set. So the process of mapping will come to end at some n, and that n will be the cardinal number of set A, cardinality of A. So finding the perfect mapping between A and a subset of n containing first n natural number gives me the process of counting, and the largest n used for the mapping gives me the cardinality of set A. Now this is very important because we are, though it is obvious for finite set, we are using same concept of counting for larger sets. So at that point, this concept of counting is very important. So again I will repeat, what is the process of counting? We will assume some subset of natural number containing first n numbers, and every time we will pick up the smallest possible natural number which is not used so far, and we will assign that number to one of the elements in first set. So pick up the first number, assign to A. Now pick up this next smallest possible number which is unused. So next smallest possible number, unused number is 2, so assign to B. Next unused number is 3, so assign to C, and so on. This is our process of counting. So what is counting? Counting is mapping, perfect mapping, finding the perfect mapping. Now if this process is going to end at some point n, then my set is called as finite set. And if this mapping is not going to end at some finite n, I will call that set as infinite set. So for this A, the process of mapping is going to end at number 5, so this set is finite. If there exists a mapping, but that mapping is not going to end at some particular n, then I will call that set as infinite set. So in this section we are going to look at these infinite sets. So you will come to know what infinite set and how this mapping will not come to end. So this will get clearer in next sections. But for the definition, the finite set, the mapping will come to end at some n, and that will be the cardinality of that set. For infinite set, there will exist a mapping, a perfect mapping, but that will not come to end, so that will be the infinite set. Okay. So in this section, we are going to find the cardinality of some big sets. So the first big set which comes to our mind is n, set of natural numbers. So let's try to find out the number of natural numbers. So before counting the number of natural numbers, let's first try to find out whether this natural number set is countable at all or not. Okay, so let's assume that we want to count the natural number. So with every tick of second, we count one natural number. So 1, 2, 3, and so on. If provided we have the infinite time at our hand, no point in time we will be stuck at the process. All the time we will be able to come up with the next natural number. Let's say at this point we have this natural number, we will add 1 to this natural number, and then we will get the next natural number. and the next natural number. Add 1 and we will get the next natural number. So this process is not going to end. So no one is going to stop us from counting the natural numbers. So intuitively, so this is the intuitive discussion about whether natural number is countable or not. So intuitively, the natural number is countable. Okay, so for the sake of continuity, I will try to count the natural numbers. So this is my natural number set 1, 2, 3 up to infinity. So for sake of continuity, I will count the natural number set with the help of some subset of natural number set. So we have already seen previously that counting actually is establishing a perfect mapping between element of set to be counted with n1 subset of n. So here what we will do, we will try to map element of this set with the element of this set. So a simplest possible mapping is 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3, this is mapped to this is mapped to this, and so on. So this n, we will come to know about this n after the process of mapping is stopped. So if this set is finite, this process of mapping will end at some particular point, and then we will come to know about this n, and that n will give us the cardinality of this set. But here the process of mapping is not going to end all the time. There will be plenty of the natural numbers, and to map with there will be plenty of the numbers in n1. So you pick up one natural number and you will find one corresponding number here. You pick up one number here, you will find one number here. So we don't have any specific n for this mapping. Since the process of mapping is not going to end, I will call this n as infinite set. So this n is infinite set because process of mapping is not going to end at some particular end. And then such mapping, a perfect mapping, man-to-man marking exists. So I will call this n as a countable set. So the set is countable if there exists a perfect mapping between element of that set with element of n1. And the set is infinite if that mapping is not going to end at some particular small n. So our natural number set is countably infinite set. Okay, since this mapping is not going to end at some n, we will not be able to come up with the cardinality of n. So what to do? So Cantor defined the number of natural numbers as Aleph 0. So Aleph 0 is one symbol he gave to the number of natural numbers. So okay, what is 5? So 5 is a symbol given to some quantity. So this is some quantity, and to represent the number of elements, this is the symbol. Again, what is 3? So I have few elements, and the number of elements to represent that quantity, this is the symbol given. Similarly, to represent this quantity, this is the symbol given by Cantor. If you don't know who Cantor is, so this entire discussion is based on normal set theory. This set theory is due to Cantor. He proposed this set theory. So now, obviously, if we have Cantor set theory, we also have some other set theories. So our basic set theory is called as naive set theory or Cantorian set theory or Cantor set theory. So this entire discussion is about Cantor set theory. So Cantor gave Aleph 0 or Aleph naught as a number for number of natural numbers. So now infinity has a symbol. Infinity has a number which is Aleph 0. Okay, I will redraw this separately. This is Aleph 0. So number of natural number is Aleph 0. according to Cantor. Now we will use same template to count the number of elements in some other